Welcome to Baozi Training Leetcode solution. So as we all know, now is the hottest season for job hunting. So if you want the best mock interview experience in North America, you have been doing interviews for a long time, but still didn't receive an offer. So we're here to help you to identify what you did good and what you could be more improved. Feel free to check us out at baozitraining.org. Moreover, feel free to subscribe to our WeChat blog. I mean, assuming you're Chinese, because everything in this blog is all Chinese. Feel free to subscribe to us. We will constantly posting very high quality articles. Alrighty. So today we're going to talk about one quick problem. It's called course scheduling. Essentially, this is like giving you n courses labeled from 0 to n-1, and they'll give you a list of dependencies. For example, here there means if you want to take course 1, you have to take course 0 first. You want to take course 0, you have to take course 1 first. That means 0 depends on 1. So the direction of your arrow head should be on the right side. 0 depends on 1. And then, so essentially giving you this dependency list to find out whether you could take those courses or not. The reasoning is, for example, you have a pair like this, directed graph. 1 depends on 0, 0 depends on 1. We all know this is a deadlock situation, or there's a cycle or loop in a graph. One thing we could quickly review here is this link. So how normally a graph is represented. So here, this article listed a few ways. One way is called edge list. So as long as there's for direct graph or indirect graph, as long as there's two edges, two vertices are connected, you'll just have one edge to connect them together. And the con part for this is just you have to loop through all these vertices, for example OM, to iterate through actually OE, if the number of edges, to iterate through whether two nodes are connected, because you can access them at a constant time. Another way is to use adjacency matrices. So this is essentially you have V vertices, you will allocate a V times V squared so that you will know whether two nodes are connected or not. Like this. For indirect graph, this is going to be a symmetric matrix, and for direct graph, it's not gonna be symmetric, not necessarily. And another way is adjacency list. So this is normally how we gonna use for representing graph. So essentially, for each of the node, those are the edges this node pointed out to, and so if you have some incoming nodes, so here it doesn't really count in there, so it will be counted under 1. For example, you have 0 pointing to 1, so 0 will be counted as 1. 1 will point it to nothing, because this is only the outgoing nodes, not the incoming ones. Well, at this point, you can think of, oh well, I could keep a input, incoming edges, incoming nodes, and also outgoing edges. You could do that. However, the cost is now you have to maintain. So whenever you add a node, delete a node, you have to find it, not just yourself. Also, you need to find whatever all the nodes you're pointing to, or you pointed to, and also update their incoming list. So it's not really necessary. I think for now, for at least for interview perspective, the way we represent the graph is just a node, and all the nodes these nodes depends on or pointed to. So if there's a node pointed at itself, at this point you won't actually know who is pointing. So for example, now I'm asking, who are all zeros? Which nodes are depending on 0 at this moment? You don't really know. You have to loop through all the nodes and then see, okay, 1 depends on 0, and 8, 6, they all depend on 0. That's the only way to do it. But you can do it the reverse way. That is, who is not depending on 0, like who is not depending on anything. And in this graph, well, they all have dependencies. Okay, let's go back to this problem. So essentially, this is basically detecting there's a cycle or not, because they didn't really ask you to print out the topological sort order or not. So there's essentially a BFS way and a DFS way. For BFS, normally we'll keep a queue, so there's going to be an extra space given, which is in terms of number of vertices, so OV, extra space. And then for the iteration, think about this. Every time when you iterate through this, you will find the node that has no dependencies, and then you will loop through all the other nodes that remove this node from it, so that if there's another node that has no dependencies, you put it into the queue. So that requires OV square time complexity for this BFS method. We'll talk about the DFS later on, but let's code this first. So this time we're going to use this awesome stuff. Okay, so here we're going to use QuarterPad for these purposes. So I set it to actually to Vim. Let's just try it. So if we just do this, we'll just run it. Okay. Hello world, welcome to QuarterPad. Okay, this is awesome. So I guess we don't need those things for now. Okay. I think. Okay, this looks good. Don't need to always save it. Okay. What I want to do is return true. No prerequisites. So is there gonna be duplicates? So for each of the node, we'll create a hash map for it, because if you only keep the ones that's showing in the list, there's no way you could actually that the algorithm, BFS algorithm I talked about, will work, because there would be no nodes that have no incoming edges. You see what I mean? So here, that's why we have to actually generate all of this in the first place, in the initialization part when we build the graph. Now we have to redeem the input. Requisites, QU requisites. First one, dependency, the next one. Okay, so at this stage we have built our graph. Now the next step is to use BFS. Test this out. The set has nothing in it. What we want to do is okay, and at the end, because when we're traversing our graph, we haven't really deleted anything yet. We only delete the children, but we never delete the node actually itself. So how are we gonna know whether we have there's a cycle or not? So basically, whenever the queue is not empty when we exit, if there's no cycle, so we should literally visit every single node already. So if there's a cycle left, so the number of nodes that are should not be 0. But we cannot just simply do like a graph.size because we, like I said, we never actually remove all the nodes. All the nodes are still there. So here we just have a course remaining equals to number of courses. So now whenever we offer it to a queue, so that means this course we have visited. Okay, and at the end we'll just see if it's 0 or not. So now what we're gonna do is the queue is not empty. This out. Notice the casting here. Only when it changes, you don't need to look through everything. Only when it decreases, you will want to check the size again, right? When it equals to 0, what you want to do is queue.offer this guy. Okay. That's pretty much it. So let's take a quick look at the code first. Finish less than that. Graph new hash set. Put it in there. Prerequisite. Queue. Number of lenses. Offer. I think it looks correct. Let's check something super quick here. Let's just say 0 depends on 1, 1 depends on 2. Okay. So there's 3 courses, and then there's prerequisites test 1, and we can have test 2, 0 depends on 1. And 1 depends on 0. And there's actually 2. Oh. Test 2. Okay. All right, let's go. symbol. Remove integer. Okay. True and false. So first one is true, the other one is false. I think this looks correct. So let's just paste it to here. Alright guys, thanks for watching. So OV square and OV space for BFS method.